Alright, so we've got this circuit. It's got 4 resistors. The total current for this circuit is 15.0 amps. 15.0 amps, the total current for this circuit. And I'm going to give you another piece of information about the circuit. I'm going to say the total voltage being supplied to this circuit by the battery or power supply or whatever you'd like to call it is 5.0 volts. I've got a few other pieces of information I want to give you straight off. I want to give this guy here, V2, the voltage across resistor 2, as 1.5 volts. I'd also like to tell you that the current going through resistor 3, I3, is equal to 4.0 amps. I'd also like to tell you that the voltage, electric potential difference across resistor 1, is 1.0 volts. And that's pretty much all I want to tell you. Now there's missing information at each of these resistors. I don't know the resistance, actually, as it turns out, for any of them. I don't know the current at this one, so that's one that I want to find out. I don't know the current at resistor 2, so I'm going to say I2 is equal to, and I'm going to try and fill in the blank. I don't know the current, I don't know the voltage at resistor 3, so I'm going to try and figure that one out. And what else don't I know? Well, I don't know the voltage at resistor 4 either. Don't know anything. Yeah, that's right. There's not a whole lot that I do know about resistor 4. I know that it's there, yeah, that it must have a resistance. Okay, so we're going to see if we can figure out all of these blanks. And notice the way that I've organized myself. I'm trying to write down what I do and don't know about each resistor beside it. Now, oftentimes you don't want to mess up a schematic diagram of a circuit. That's okay, just redraw it and mess up the one that you've redrawn. But it's fruitful to sometimes have what you do and don't know about each resistor labeled beside that resistor. Help you to think through the process of what you can use and what you can't use. First of all, could I figure out, you know what, this wasn't something I was going to ask, but if I know the total current flowing into a circuit and I know the voltage for the whole circuit, could I figure out the resistance for the whole circuit? How? Is there a law? What's the name of the law? Yeah, Ohm's law. Ohm's law. So I could use Ohm's law for these values here for the whole circuit, and I could say, all right, well, Ohm's law says that V equals I times R, so it must be true for the whole circuit as well. V total equals I total times R total. So I could say that R total is equal to V total over I total. Subbing in my values, V total is 5 volts. I total is 15 amps. 5 volts, 15 amps. Oops, amps. Units are going to work out. 5 over 15, it's 1/3 if you reduce it down. So we could say it's 0.3 repeated ohms. Or we could just say, well, there's 2 sig figs here, so 0.33 ohms approximately. That's the total resistance, and we could put it in there. 0.33 ohms. Now that's the approximate value, so I'll put a little dot over the equal sign. That's one value down. What about current 1? Can anybody logically deduce what current 1 must be? Yeah? Sorry? Why would you say 15? Yeah? Yeah, it hasn't branched off yet, right? Hasn't been any branches, no new pathways created, so the current hasn't been forced to take multiple routes or anything like that. So if we were drawing the current, let's brainstorm ahead now. The current must have stayed the same at this point, and by the time it gets down to this branch, some of it goes this way, and some of it goes this way. Yeah? So Joe says that I1 and I total must be equal because of that rule that for series circuits all the currents are the same. So far we're staying in series, so I total and I1 should be the same. So we're going to say that this is equal to 15 amps by that logical process. And some of this stuff is just logical process based on the formulae that we know. Now we get down to this point here. Let's talk about current. We just said that it branches off in two directions.
7.5.
Jumping straight to the 7.5. Are you sure?
I'm so sure.
Well, let's find out. Let's find out. What would the logic be?
Because it has to split out in two to go both ways.
Okay, so some has to go one way, some has to go the other way. So I could say, all right, I total is going to be equal to the current that goes down branch 2 plus the current that goes down branch 3.
Oh wait, no, I want to change banks.
Okay. I thought you might. It's okay. I didn't want to say you're right or wrong yet. All right, I total. I could plug in my values right away, or I could just isolate for the value I'm looking for. I'm looking for I2, so I'm going to say I total minus I3 is equal I2. Now I can start plugging in my values, and I can say that I total is equal to 15 amps minus I3, which is 4 amps. What do you say?
11 amps.
11 amps, yeah. That's okay. I figured you knew what was going on. Maybe some chose the wrong numbers for the head math.
That's right.
All right, 11 amps. Let's label it up. Now, we might as well finish off the current stuff. We're on a roll with current. After the current's gone down these two branches, it recombines again and comes out of the junction and follows along the rest of the circuit. What must be true of current 4?
15. Same as current 1.
Same as current 1. And by that logic, I could just say that it's 15 amps. Okay? Now let's go back and talk about voltage. Remember, we had some analogies with waterfalls. And we could say, look, this is a parallel junction. What must be true about all the voltage drops across each branch? Should be equal. For parallel junctions, all the voltage drops across the branches that are running in parallel should be equal. So in this case, the voltage for the entire junction, we can call it V total for the junction, or we can call it VA. Let's call this junction A. Junction A. VA would be equal to V2, which is equal to V3, because it's a parallel junction, and so V3 must be equal to 1.5 volts. Now, what's the voltage drop across junction A? 1.5 volts. So if I took a voltmeter, look at this, if I took a voltmeter and I measured from one side to the other side, what would the voltage be across that? 1.5. So, fair enough. But the reason I bring that up is this. I've got how many volts of energy per charge to use up here? 5 volts. How many do I use up on the first resistor?
1.
How many do I use up across this junction?
2.
Be careful. You just told me 1.5. The whole junction uses up 1.5. It's one waterfall. 1.5. So 1, 1.5. How many do I have left over to finish at that resistor? 2.5? Do you see that? So I could say V total is equal to, well, should be equal to V1 plus VA, that's the voltage across the junction, plus V4, and I can solve for V4. V total minus V1 minus VA equals V4, or 5 volts minus 1 volt minus 1.5 volts is equal to V4, and you people just told me it was what again? 2.5, yeah, 2.5 volts. Now before I go on to resistances, because we can calculate the resistances now too, we have enough information. Before I get to the resistances, I want you to notice something. Some people talk about using voltmeters across junctions like this to say, hey look, the voltage across this whole junction was 1.5 volts, let's just treat it as one junction. Some people talk that way. Some people talk about following an electron on its journey through the pathways. So let's see what happens if we just follow one electron and treat this like a maze. I've got this electron that starts off here. Well, sorry, it's conventional current flow, so I've got this positive charge, but suspend your disbelief, okay? We've got this charge that leaves here. At this point, the charge loses 1 volt. So we're down to 4. Then we come here, and every charge has to make its choice in life. And let's say that this charge goes this way. So how many does it lose going this way? 1.5. Now we're down 5 minus 1 minus 1.5. We're down to 2.5. Then we keep on going, and we go around here. We use up the last 2.5. That's if the charge went that way through the maze. Every circuit's like a maze. You got to choose only one path. A given charge only takes one pathway. That only makes sense. So let's try another option. We go this way, we lose 1, we're down to 4. We go down here. This time, we turn the other way, this way. How many should you lose there? 1.5. And we keep on the maze. We lose our 2.5 there. So, I mean, it's kind of a matter of preference, I suppose. Personally, I think following the pathways gets you to a better understanding of what's really going on here, because they really are flowing charges going through pathways, and for any given pathway, you're using up all of your electric potential energy per charge. But if you want to talk about it as saying the summation of this, plus the voltage across the junction, plus the voltage across that resistor, I suppose it works mathematically. It just doesn't get quite to the concept yet. Anyway, let's get to the resistors. If I wanted to find the resistance for R4, how could you do it? Do you know a law? Not Kirchhoff. Ohm. Highly meditative law. R4 should be equal to V4 over I4. And if you plug in the values, you should be able to use Ohm's law with the given V and I value for that particular resistor to figure out what the resistance is. What is it?
1/6.
Is it 1/6? Yeah. Could be. 1/6. What does 1/6, 2.5 over 15, work out to in decimals? 2.5 divided by 15. Come on.
You got that right though.
Okay. 1.6 repeated, or we could say rounded to 1.67. We know it's going to round to approximately 1.7 ohms. There's 2 sig figs. 1.7 ohms.
It's 0.1.
Oh, sorry. 0.166666. Sorry. 0.17 ohms. My fault. 0.17 ohms approximately, or 0.166666 ohms. Let's find it for R3, R2, and R1. Okay? You guys go. Take a minute, find R1, R2, and R3. They won't be the same. As it turns out, these resistors are not identical. You wouldn't know that until we did this analysis. I'm just filling in the values, and if you want to check them, you can. Try and calculate along with me. Okay, so we've got approximate values. R1 should be approximately 0.067 or 0.06 repeated actually. R2 should be about 0.136 ohms, and R3 should be about 0.375 ohms. Now, I want to go back and look at that for a second in terms of or along with the current, because I want to see if we can make sense of this. We've got the resistances are all correct. Maybe there's some disagreement about sig figs, but we've got some approximately correct values here. I want to look at the current. Which one has more current flowing through? We've got 2 branches. Branch 2 or branch 3? Definitely more current. Now look at the resistances. Let's see if it makes sense. Which one has more resistance? Now if you got more resistance, does it make sense that you'd have less stuff flowing through it?
Yes, sir.
Why not? So this even makes conceptual sense if you try and compare it to water pipes or something like that. But there's a restricted flow there because of the higher resistance. I want to give you guys some problems that are like this, but I'd like you guys to try it. I don't want to hold your hands through it. I would like you to work on it with a partner. You got to work on it with a partner so that you can bounce ideas off of each other and work through the formulas together. Okay? Now I'm going to come around and circulate, but it's going to be some good practice for the exam.